the odd powers of the cosine. What happens if we have an odd power of the cosine? Remember, we are looking to integrate the product. So if the cosine, the power of the cosine is odd, then n equals 2k plus 1, where k is an integer. So if an n, therefore, is forced to be an odd integer by multiplying an integer by 2 and adding 1. And I can break it down in the following manner. I can say that the product, the integral of sine x to the n power times cosine x to the n power dx, if n equal 2k plus 1, then I replace it with the following. And this is what's going to happen. Here I can write it as sine. Stuff that I'll have to rewrite. Breaking down, cosine x to the power of 2k plus 1 can be written as cosine x to the power of 2k times cosine x by itself dx. And this is what I have, and this is my goal. I want to have cosine x dx. Okay, so that's the principle behind this activity. And now let's see what I do with the rest. So I'm settled with the differential. The rest, I'm going to use some trigonometric identities. So cosine x to the power of cosine x to the power of 2k can be written as cosine x squared to the power of k. What is the advantage in doing so? Remember, I have the differential cosine x dx, which is, once you take the antiderivative, it's the sine. So I need everything else in the chain to be written as the sine in terms of the sine function. Well, if I have, that's why I said that we're going to start. If we start with odd power of cosine, and you take you take cosine x out of it, then you are left with an even power. And even power can be written as cosine squared to another power, and the cosine squared can be substituted with 1 minus sine squared. So this expression can be written as 1 minus sine squared to the power of k. And once you do this substitution, then what you're left with is a radicand that contain only terms of sine and the differential that has cosine x dx. Okay? So at this point, we'll go back to the way we started. We'll have a substitution. So we let u equal the sine x. And of course, du equal cosine x dx. That was the whole idea. That's why we want to have only stuff that has sine x in it. So now the integral, since I'm breaking the equation, let's call this integral I. I will stand for a generic integral. So going back after the substitution, I, the integral, will be, instead of sine to the power of m, we have u to the power of m, and then here we have 1 minus u squared to the power of k, and then we have du. and we solve that. And so in summary, we can say that if we have odd power of cosine, those of you who like to remember formula, which I in principle against this approach, but sometimes it helps people just to memorize stuff. You can write it as u to the power of m times 1 minus u squared to the power of k du. I strongly recommend that instead of memorizing the formula, go over the process. There is one basic principle, is having a differential that is with a known antiderivative. For instance, the integral of cosine x dx is sine x, the integral of sine x dx is negative cosine x. What other differential we can be used as we do this stuff? What is the derivative of the tangent? Come on, give it to me. Secant squared. So if we want to solve stuff that contain tangent, we want to have secant squared dx at the end, right? Because we know how to integrate that. So this leads to a combination secant tangent. What about the derivative of the cotangent? Cosecant squared. So if you have a differential at the end that read cosecant squared theta d theta, you can use that to solve a product of the cosecant and the cotangent, similar to the product of sine cosine. And this is the idea. So if you understand the idea, then you really don't need to remember a formula. I'm going to give you an example, a very simple example, and I'm going to do it twice. I'm going to use the formula the first time, and then I'll use the principle the second time. And hopefully this will convince you that the principle is more important than memorizing the formula. All right? The first one, so we call it example 1, and this is, well, actually I call it, forget about the A, I'll do it twice. Okay, what we need to evaluate is the integral of the cosine cube of theta d theta. Okay? This is cube. So let's see, solution number 1. I want to use the formula. I'm going to write cosine cube of theta d theta. Since I'm looking for a product, right? The formula is a product. Well, I don't have a sign here, so I'm going to write it as sine of x to the power of 0, just a matter of formality. Cosine x to, instead of 3, I'm going to write it as, well, let's write it as 3 for the time being. Okay, so we're looking at m equals 0 and 2k plus 1 equals 3, and therefore k equals 1. So plugging in the formula right here, then the integral of sine theta to the power of 0 cosine theta cube d theta by the formula will be the integral of u to the power of 0 1 minus u squared to the power of 1 du, and I can write it as the integral of 1 minus u squared du, and the result of the integration will be u minus u cubed over 3 plus c. And then u is a cosine, right? That's how, u is the sine, I'm sorry. That's what we had here. So the result will be sine theta minus sine cube theta over 3 plus the constant c. Okay, this was solution number 1. Solution number 2, again, by substitution, because that's what we really do. But what led us to the substitution is the following. We broke down cosine cube into cosine squared times the cosine to get to the differential cosine theta d theta. Okay? And then we substitute the cosine squared with 1 minus sine squared d theta, cosine theta d theta. And now we have either u or, we can write it again as we let u equal sine theta, and therefore du equal cosine theta d theta, and the integral of cosine cube theta d theta becomes the integral of 1 minus u squared du, and this equals to u minus u cubed over 3 plus c, or almost out of space, sine theta minus sine cubed theta over 3 plus c. So I prefer the second approach, because what was the principle behind the second approach is that separation. That the idea that if I have cosine cube or cosine to the 5th or cosine to the 7th or any other odd power of the cosine, I can split it into an even power plus the differential cosine theta d theta. And likewise, you can imagine we'll do the same thing when we'll deal with the odd power of the sine.